Hello and welcome to Chapter 2. This is called Chemical Physiology. Now, that sounds kind of, um, shall we say, what's the word? Erudite is the word. Yes, super knowledgeable, super technical. What we're trying to do here, I understand that many of you may not be necessarily biology majors, but if we're going to go into healthcare, you do want to have some awareness of this because this is part of the healthcare process. You may be involved in a, shall we say, a non pharmacological situation, but as a caregiver, and that can be as a parent or as a loved one or as a friend, never mind being professional, having some awareness is going to help you a lot in understanding why you may choose to do certain things as a clinician or other clinicians may recommend or choose to do things in terms of interventions and so forth in either patients that you're working with or your loved ones or friends. So let's dive into this. I'm going to try to keep this as as accessible as possible. I've worked really hard on this. I know that it may or may not work, but I want you to know that I've thought a lot about trying to give you what I think you really need to be a more well-rounded caregiver. Before we delve into the topics that we're going to delve into, and I'll give you the list of some of the things we're going to shoot for in this chapter, it wouldn't hurt you if chemistry is not your bag of chips, shall we say. It wouldn't hurt to go and review some of these concepts. Either look at your old notes or go in and look at ion transport a little bit. Well, that's from a lot of that's from 165 or basic chemistry solutions. Logarithms and pH. I'll try to break that out a little bit. Logarithm is a kind of a scary word for something that actually makes life a lot easier. It's just a type of annotation. We're going to talk about it when it comes to pH. If you remember acids, bases, and buffers, I do have some slides based on this in this presentation. So that one we'll actually talk about a little bit. And then the different biomolecules, it wouldn't hurt to refresh your understanding of those. We'll get into chapter 3 a little bit on this, but if you want to speed up the process, maybe review, especially Bio 165 if you've taken that course. On a conceptual level today, we are going to use the information that I'm going to provide you in order to help you understand more about non-covalent interactions, that is to say, the non-covalent bonds that give rise to things like protein structure, which then gives rise to protein function, which gives rise to cellular function and tissue function, and so forth, as well as interactions. That is to say, how is it, and then why is it that proteins do what they do? How is it that they bind together and dissociate or aggregate, et cetera, et cetera? So we're going to use the concepts today to get after those two major ideas. If I haven't said this already, one of the goals of a physiology class is not only to learn the processes, there is some of that, but also understand and be able to discuss and interact with other people regarding those processes, whether it's your patients as an educator. Okay, patients do better when they have good information and you're going to be conveying that information to them, or as collaborators and colleagues in the healthcare and professional environment. So that's what these goals are about, is to help you develop your vocabulary, your conceptual understanding so that you can interface and relate information more effectively. So we're going to talk a little bit about bonds. The given bond that we're really just going to touch on is the covalent bond. We're not going to delve into that too much. Organic chemistry and some other classes deal with that. Where we're going to spend more time is going to be on the non-covalent bonds. This is ionic, hydrogen, and van der Waals, also known as a hydrophobic interaction. So we're going to talk about those, especially in the context of protein structure. So you do need to be able to recognize and describe the four levels of protein structure: primary, secondary, tertiary, and quaternary, and importantly, what bonds are involved. This will give you some insight as to why we in the clinic will spend so much time looking at certain parameters in patients, especially in acute care. Part of why we're delving into this is because of the supremely important relationship between molecular shape and function, proteins in particular. And let me give you just a crude analogy. Let's say you've got a bicycle and you're riding your bicycle. Those wheels aren't perfectly round. You've changed the shape of those wheels just a little bit, so it's not perfectly round. That's going to drastically affect the performance of your being able to ride that bicycle. Much less if you turn those circular wheels into, say, triangles. Okay, that might shut that bicycle down altogether. All right. So understanding not only that we can change function, but also how well a function occurs is something that I want to continue to reinforce with you guys. Along those lines, pH. We're gonna get into the concept of pH and why it is so incredibly important. It's an example of one. Certainly, ionic concentrations, temperature, and other things can be important as well. But pH tends to kind of rise to the top. And so we'll discuss that a little bit. Different functions of proteins. This is a little more memorization. So what do soluble proteins do? I've got a list of those to be able to recognize, what a soluble protein might do from the list, and what an insoluble protein is, and generally what they do. And we're going to, in chapter 3, we'll get into a little bit more of that, maybe in chapter 4 and 5 as well. And then lastly, we're going to get into interactions. This is a much, much bigger topic, and I'd love to spend more time on it, because I think the more time that you do spend on it, the easier things get down the line. The easier it is to handle larger volumes of material. But we're going to get into the key concepts. That is the idea of binding. Again, back to this idea of non-covalent interactions. The difference between a ligand and a substrate, I'm going to break that out a little bit. And then this last little concept, which tends to be more mathematical, is this idea of affinity and a concept we call law of mass action. Law of mass action. You might want to write that down. So let's get started. So why dedicate the time to this stuff when we could be moving into more what feel like more relevant topics? That a lot of people come in to this class questioning, why do I have to learn this? Because this is where the action is. Everything that you do clinically should be rooted in, we are biochemical organisms. So having some awareness of this will again tailor how we handle disorders and so forth. Things like why we have curly hair versus straight hair. We think a lot about neurons and the neuromuscular interface. Certainly muscular contraction is a big deal, but equally important is endocrine signaling. And we take advantage of that endocrine signaling using exogenous compounds, pharmaceuticals. Certainly understanding enzymes, a lot of disorders and a lot of problems in patients are enzymatic in nature. For instance, hemophilia, your blood doesn't clot properly. That's an enzymatic issue. More and more, we're understanding antibodies and immunity, whether we're talking about vaccinations or we're talking about therapies for cancer. There are more and more antibody-based drugs. I'd love to spend more time on immunology, and I think if you're going to go into healthcare, immunology is a really great topic to study. Genetics and so forth. A lot of stuff. All this stuff is based on the concepts we're going to talk about today. Whether it's injury and pathophysiology or treatment, whether we're doing manipulations, putting things on patients, casting, training, pedagogy, all of medicine often involves modulating protein function in particular. If you've ever been involved in acute care or emergency care, or observed patients in emergency rooms, so forth, one of the things you'll often see, or if you're reviewing a patient's chart, you'll see these Chem 7, Chem 8 basic metabolic panels, if you will. So why are these considered to be so important? These ions and these functional molecules, why are they so important? Because that's how the cells get the job done, is using these different types of molecules. Things like ions and things like pH. So we want to talk about those things a little bit today, especially pH. We're gonna give some lip service to ions, but especially pH in this lecture. And so those ions and pH all help modulate protein shape. And if you look at this picture here, you can actually see a membrane here, and there's a cytoskeletal element here, and some kind of a globular protein, and so forth. This was a really amazing. It's an artist rendition of what looks like an organelle. There's an organelle here, and membranes, because all of these structures, well, even if they have, like, for instance, phospholipids, like in these membranes here, nevertheless, proteins are at the core of a lot of the function of these things. So we're going to delve into that topic today. So we have four major categories of bonds. We have covalent bonds, which involve the sharing of electrons to create a very strong bond. Mostly what you want to be able to do is recognize these solid lines between these atoms as a covalent bond. Maybe talk about that a little bit later when we get to disulfide bonds. We have ionic bonds, which are stabilized by having opposite charges on the side groups of amino acids, particularly in proteins. We have hydrogen bonds, which are not covalent, not ionic, but they have elements of both a little bit. Then we have the most nebulous, which is called the hydrophobic interactions, of which van der Waals is one of them. This is what gives oil and things like graphite its excellent lubrication properties, because these individual molecules here can slide across each other. It's the weakest of the forces. Starting with ionic bonds. Ionic bonds involve ions, if you will. That is to say, like, for instance, an atom that has lost an electron, like, for instance, a sodium atom, if it gives up an electron to, say, a chlorine, all right, that chlorine is going to hold on to that electron and not let sodium have any access to it. And so now we have a negative charge on the chlorine and a positive charge on the sodium, and that would give us sodium chloride. And that's an ionic bond, because these two now ions are attracted to each other by virtue of their charge, the basis of their charge based on the ratio of electrons and protons. Opposite charges attract, identical charges push apart. And we'll get to that when we especially get into resting membrane potential. This has relevance in proteins. Protein amino acid side chains can, in aqueous environments, lose or gain charge. If they're acidic or basic in nature, they may give up a proton and thus have a negative charge, or maybe the accepted proton have a positive charge, and that can create interactions that stabilize structure in proteins. And those are called ionic bonds in proteins. And that's why ionic concentration in intracellular fluid or in the blood, back to our chem panel picture, that's why ionic concentrations can be really important, because they have an effect on protein structure. And for delineation purposes, in terms of image, you should be able to recognize an ionic interaction in a protein. So here it's a little hard to see here, but there's a plus and a minus here if you look closely. If you see that plus and minus, as opposed to say a dotted line or a solid line, this is a covalent bond here, a disulfide bond. This is a hydrogen bond right here. This plus minus, that's your indicator that you have an ionic bond, ionic interaction going on, either inside a given protein or associating with multiple proteins, or a ligand substrate type interaction. Above and beyond proteins, we do have very important ions in the body. And so you should be able to know what these and be able to recognize these. Sodium, potassium, calcium, hydrogen. These are all elemental ions. Chloride is in there as well. But you can also have multi-atom ions, like, for instance, bicarbonate, which we're going to talk about more later on in the semester. Phosphate, when we talk about protein modulation, is super important. Sulfates, I won't talk too much about those, but these are all really, really important ions above and beyond protein structure. Yes, they will influence protein structure when they're in extracellular fluid, but they also have individual functional roles as well that we're going to touch on moving through the semester. Now on to hydrogen bonds. Hydrogen bonds are a polar bond. They are a polar interaction, but they are neither covalent nor fully ionic, and they have very, very specific parameters. In biology, the hydrogen bonds we're talking about involve a bonded oxygen or nitrogen. There are other types of hydrogen bonds out there. They include fluorine and other things, if you get into inorganic chemistry. But in biology, then the vast, vast majority are going to involve either an oxygen or a nitrogen atom and a hydrogen. So here are two water molecules, and so here's that bonded oxygen, and it's slightly negative. That's what that delta negative means. A little delta negative means that there's a slight negative charge there. The electrons are hanging out with these oxygens a little more than they are with the hydrogens. That means the hydrogens, though, still have a little bit of, that means they have a little bit of positive charge, and so there's an interaction there. And this hydrogen bonding is what gives rise to these emergent properties of water that make water the molecule of life, if you will. We have trouble visualizing the possibilities of life without a molecule like water. The fact that ice floats and doesn't sink, the cohesive and adhesion and so forth. But hydrogen bonds are super important in DNA structure. We have the double helix, if you will. One strand on one side, another strand on the other side is stabilized by hydrogen bonds. And you see these little dots here between these, either a nitrogen or an oxygen and a hydrogen. Super duper important in protein folding. All right. When we get to the different structures, secondary, tertiary, and quaternary structure, hydrogen bonds are going to be very, very important in those structures. And lastly, the van der Waals, I tend to just summarize that and say hydrophobic interactions. These are the weakest, and again, it's the force, or it gives rise to the properties of things like oils and non-aqueous lubricants, because these electrons are flowing in and around the molecules, and so while there is some adhesion, nevertheless it's a very, very loose association. So van der Waals is the most common, and we call these interactions hydrophobic. For instance, these fatty acids that are depicted in this membrane structure, this phospholipid bilayer, we have these polar head groups. These are more attracted to water and hydrogen bonds and so forth. But you have these non-polar fatty acids that are attracted to each other because the electrons can flow between them. That's that hydrophobic interaction. We're going to talk about this from time to time. Especially in chapter 5 with the membrane interactions and so forth. In protein structure, they add another layer of stability to a protein. So if we take a protein and we subject it to differing forces, if you will, what you see is you have this beautiful helix here that begins to disintegrate as we add force to it. Now, this is with van der Waals forces. Now, the experiment was done where they were able to substitute, and so you didn't have van der Waals forces. And what you see is the destruction of that beautiful structure is far more enhanced when you don't have those. So it's a subtle thing, but it's an important one. And when we get into hydrophobic interactions, when we're talking about especially membrane transport. So now that we have the bonds set up, how these bonds affect protein structure. Now, these two images are actually the same protein. One's looking at it from the top. This one's looking at it down the axis from shall we say this direction. So we're looking at the same molecule. And why does it have this shape? Chemical bonds. This slide here again is to remind you that you need to be able to recognize these bonds in situ. For instance, we've got the covalent bond over here. You can recognize it in proteins as a single solid line. Yes, there are double bonds and triple bonds out there, but you never really see those. To my knowledge, I've never seen a double bond in a protein. So they're always single bonds, and this just happens to be a disulfide bond, two sulfurs linked covalently. Here's our ionic bond. And again, it's a little hard to see here, the plus and the minus. You might see it down here in this picture where you have a plus and a minus. That's an ionic bond. Over here on the right, the dot, dot, dot between either the oxygen and a hydrogen, or it could be a nitrogen and a hydrogen. It's represented with dashed lines here, dash, dash, dash. Those are hydrogen bonds. And then van der Waals and so forth, very, very difficult to annotate. What you see are a bunch of amino acids aggregating. We usually just, point to it and go, this is where you're going to have a group of hydrophobic interactions. When we talk about carrier proteins and some of these things in the blood, hydrophobic interactions become very, very important. As we recognize the bonds, we also have to be able to recognize the different levels of protein structure. And so we have 4 levels of structure. We have 4 bonds. Now, it's not one bond per structure. Each structure has an individual array of one of those or more of those 4 bonds. So let's break this out. We have primary structure, which is the linear sequence of amino acid monomers that are linked covalently. These bonds, by the way, between these amino acids are known as peptide bonds. There are very, very specific proteins that can cleave peptide bonds, as opposed to, say, sugars, which is also a covalent bond, but it's a glycosidic bond. But in any case, it's the linear sequence of amino acids, and the only bond involved in this is a covalent bond. That's primary structure. Then we take that primary structure and we can either create a helix, or we can create, and it's not shown here, more of a zigzag sheet that's flatter, more of a sheet-like as opposed to a tube. That's called secondary structure, and that is hydrogen bonds. Hydrogen bonds all the way down. So hydrogen bonds stabilize whether we call it an alpha helix, like here's an alpha helix here, and then we turn and there's another, and that so forth. This is tertiary structure. So we take these individual either helices or sheets and begin folding them around into a 3-dimensional structure called tertiary structure. This happens to be a globin protein with a heme molecule stabilized inside there. All right. Well, this is tertiary structure, and this one has ionic bonds and hydrogen bonds and van der Waals hydrophobic interactions. and the occasional disulfide covalent bond. So it has all four bonds. The disulfides tend to be the rarest, but the other ones are the ones that are the big drivers of this three-dimensional shape called tertiary structure. Then we have what's called quaternary structure. So if we take this globin protein that has a heme in it, we've got four of those here. Four globins per hemoglobin structure. Now, each of these globin proteins is associated with the other globin proteins non-covalently. If they were covalent, then they would be considered one molecule, one protein, but they're non-covalently linked. All right, that means ionic, hydrogen, and hydrophobic van der Waals. And so a complete hemoglobin structure has non-covalent interactions that bring these four globin proteins together along with the hemes that are inserted into those globins. So that's quaternary structure. The only bond that is not generally involved in quaternary structure is a covalent bond. Now that we have the basic components of what determine the basic shape, we can now begin trying to link that shape to function. Now, this is a little bit tricky because shape isn't constant. Shape can either vary by how the protein is created, but also how the protein is regulated and the environment that protein exists in at a given moment. So it's not just a static thing, it's a dynamic thing, and that's can be sometimes kind of hard to visualize. Proteins do have complex and varied shapes. That can be due to their primary structure, but also secondary, tertiary, and quaternary, and that's a dynamic process that can change over time. So if we have these basic functions of proteins here, whether they're enzymes or receptors, et cetera, we're going to be talking about these terms, so you might want to get familiar with these things. These shapes dictate these functions. If we don't have the proper shape, then what would be an enzyme can't function as a catalyst. And these shapes can change based on the environment, whether we change the chemical bonds by modifying the protein, or the environment in which the protein is located. And let's go after the big daddy of them all. And the big daddy of them all, at least in terms of this class, is hydrogen ion concentration, pH. All right. pH is just a logarithm. It's an inverse logarithm, if you will. That is to say, the lower the pH number, the more hydrogens you have, the stronger the acid. And that has a profound influence on molecular shape, especially proteins. We can see it in DNA as well. Not so much in carbohydrates, maybe a little bit in lipids. But when it comes to proteins, this is really pretty much king. It's the measure of free concentrations of hydrogen ions. And again, the lower the number, the more acidic it is. The higher the number, the more basic it is. All right. And these are aqueous situations. And so, again, anything below our magic number in our cells, and our magic number in our cells is a little bit on the alkalotic side. It's a 7.4. That is the ideal pH in our blood. It actually ranges. It's a homeostatic window, 7.35 to 7.45. Anything below 7.35 is the clinical definition of acidosis. So a lower number, 7.3, 7.25, getting dangerous. On the other side, if we start to get above 7.45 to 7.5, 7.55, 7.6, we are undergoing alkalosis. We are becoming more basic. All right. So be able to understand that concept, understand what pH means, and the magic number here and what happens when we shift. A lot of our compounds in our bodies, that includes ions as well as proteins, serve as buffers. That is to say, they help prevent us deviating outside of this range of 7.35 to 7.45. This is just a figure from your book. It gives you a little bit of a designator in terms of why when we talk about an acid tends to create more or protons in the aqueous solution, usually by donating a proton off the molecule itself. Like here's a carboxylic acid giving off a proton, making the solution more acidic. A base does the opposite. A base will remove protons from the solution. In this case, this molecule is giving up a hydroxyl, which then reacts with the proton to form water. All right, so what's happening is the net concentration of proteins is going down. When it comes to proteins and other molecules, oftentimes you have functional groups that will absorb that proton rather than creating a new water molecule. They just pull that proton out of solution, and that means that they are functional bases, if you will. Don't want you to get too wrapped up in this. This is a little bit of an aside for some of our chemistry majors, but just to understand what it means to be an acid and a base. An acid will cause proton concentrations to rise. A base will cause proton concentrations to fall. Okay, we're at about the halfway point, a little more than halfway. Just a quick review of what we've been talking about. Non-covalent interactions in particular, ionic bonds, hydrogen bonds, van der Waals hydrophobic interactions, how they contribute to protein structure. We drilled down on pH a little bit and how it affects the shape. Again, the different layers of protein structure. The reason that pH becomes so important is because it can affect secondary and tertiary and quaternary. It's one of the few that can affect all three of those. Primary is a covalent situation, but there are no other bonds that are involved at so many different levels of protein structure, and that's why pH is so important. So we have two families of proteins. We have soluble proteins and we have insoluble proteins that tend to be fibers, if you will, connective tissue, et cetera, cytoskeleton. Soluble proteins have all of these potential functions, and the main thing here is to be able to recognize what these terms are and that these are actually the role of soluble proteins, whether it's catalysts in chemical reactions, metabolism, whether we're talking about channels and carriers, signal proteins, and so forth. So be able to recognize these as soluble protein functions. Immunoglobulins, that's just a fancy word for antibodies involved in immune response. Insoluble proteins tend to be more structural, that is to say, cytoskeletal, extracellular matrix, and so forth. And that makes sense, so that they shouldn't be floating around in an aqueous solution. They need to be insoluble, and so that's what we talk about there. All of those functions, whether we're talking about soluble proteins or insoluble proteins, require interactions, and then we call those interactions binding. What does binding mean? How do we define binding? It's almost always an interaction that involves non-covalent bonds, because if we make it a covalent bond, that generally, by definition, makes it a single molecule rather than multiple, a dynamic interaction. So we're talking about non-covalent bonds and interactions with other molecules. They could be other proteins, they can be ions, lipids, DNA, you name it. Where those interactions occur, we call a binding site. All right, so a binding site is where that protein will interface or interact with another molecule, whether it's an endogenous molecule or even an exogenous molecule like a drug or pharmaceutical. This binding, because it's non-covalent, will go to, or shall we say, attempt to go to what we call a state of equilibrium, where there is as much binding as unbinding. So the rate of binding and unbinding becomes equal. That's what we mean by equilibrium, that we are moving in both directions in relatively same rate. A quick definitional issue here that sometimes pops up, especially folks who've taken biochemistry or are chemistry majors. What is the difference between a ligand and a substrate? A ligand is something that will bind with a protein but is generally not chemically changed. All right, now there are some discrepancies here. I want to be really, really careful about this, but in this class, you may not even agree with this definition, but you're going to have to agree with it for purposes of this class. Is that a ligand is something that will bind to a protein that is not fundamentally or chemically changed, if you will, versus a substrate. A substrate is changed as a process of the interaction with the protein. And proteins are specific about their binding. They're relatively specific. They're not exclusive. All right. For instance, you have opioid drugs that will bind to opioid receptors the same way that opioid peptides will bind to receptors. So the receptor can bind not only the opioid, but also the opioid peptide. If you want to get a better handle on this, this is a great link, and I strongly suggest you check it out. It's worth your time. It's just a couple minutes. So here's an example of binding. In this case, we have a ligand here. Now, this could be a substrate, but remember that a substrate gets changed. So in this case, this ligand is binding this binding site non-covalently and will attempt to reach an equilibrium. Now, the cellular processes often prevent equilibrium from being reached. We'll get into that a little later. But for now, what we're going to say is that this binding and unbinding, when it reaches equilibrium, the ligand is disassociating as quickly as it's associating. It's relatively specific. It is, or generally reversible, and it's non-covalent. All right. Here we have ligand. Let's talk about substrate. When it comes to substrates, on the other hand, the result of the interaction is a change in the status or the chemical makeup of the molecules involved. So here's our protein. It's binding the substrate. Same exact process as ligands. Non-covalent most of the time. There are some rare exceptions. Non-covalent interaction, you get that binding. That then leads to the protein altering that molecule, in this case, creating two products. That is the essence of the difference between what makes up a substrate as a ligand. If this were a ligand, it wouldn't be changed. And so that's what we're showing in this picture. Here, the ligand and the substrate are both binding. In the case of the ligand, it's binding what we call a binding site. All right. In a substrate binds, that binding site is now called an active site. Okay. So we're trying to bring some of this mishmash of terms around because sometimes substrates and ligand terms get used interchangeably. But we're going to try to lock it down for purposes of this class, that when something binds and is not changed, that's what we call a ligand, and it binds a binding site. And when that whatever molecule is going to be changed or altered in some way, it's going to be the active site, and it's a substrate. And we're going to test you on that. We're going to test your conceptual understanding of that. This slide summarizes what we've just talked about in terms of binding versus ligands and substrates. Non-covalent interactions, they occur at a binding site. If it's a substrate, we call it an active site. It's going to attempt to go to a state of equilibrium. Whether it gets there or not is an open question. And again, they'll be situational, so we'll talk about that a little bit, especially in chapter later on in this unit. Specificity, not exclusive, and there is something we want to talk about within what's called induced fit. So this is a term we want to define for you here real quick, and then talk about affinity, which is gets into something called the law of mass action, which is a major concept in this first unit. Just a quick concept to define here. It's called induced fit. Induced fit says that if you have a protein that's going to bind something, in this case, these things here are being changed, so that makes them substrates, and so A right here is going to be the active site. So notice that there's a certain shape here before binding, and then once we bind, that shape changes, and we get some reaction. In this case, we're going to create a covalent bond here. That's induced fit. You see, the shape changes as a process of the binding, and this can be due to this can happen in enzymes and substrates, but can also happen in receptors and ligands. So again, here's the enzyme substrate example. You notice that the shape isn't perfectly round, not perfectly V-shaped, but once that substrate binds, that shape changes in that protein and then causes an alteration to lead to products. Induced fit model here. So boom, you see that catcher's mitt closing. In this case, the ball isn't being changed, right? So that would make the ball a ligand and the inside of that catcher's mitt a binding site. But notice what happens. The ball comes in and the catcher's mitt closes. If that catcher kept that glove open, the ball would basically bounce off the mitt onto the ground. All right. So that's an example of induced fit model for, shall we say, a protein ligand binding, as opposed to, say, a protein substrate binding. The final piece of the puzzle involves what's known as the law of mass action. I haven't put this on the slide, but we want to call it I think you should write this down, the law of mass action. You will see it in subsequent slides. The concepts of law of mass action and the larger concept of affinity are going to be the last part of this lecture today. And in this figure here, we have a molecule that's binding a protein. In this case, looks like it's going to be a ligand. I can't tell from this picture. Over on the left, we have strong binding, okay, some hydrogen bonds going on here, probably some other ones could be as well. That's strong. Over here on the right, it's not as strong because there's water involved and some other inner things going on here. That's a weak binding situation. That's getting after affinity and law of mass action a little bit. They're two different concepts, but they do work together. And so let's break these out over the next few slides. So when we have the potential for interaction between a protein and a ligand, or it could be a protein and a substrate, as I mentioned before, that interaction will attempt to achieve equilibrium. The cells won't always allow it to do that, but we're going to attempt it. That is to say, we're going to attempt to get to a point where the rate of binding is equal to the rate of dissociation. And that's a ratio, all right? Every reaction out there has a different percent which will be bound and unbound, and that's rooted in affinity. Law of mass action says that we're going to attempt to achieve equilibrium, and that percentage of what's on one side or the other is the function of affinity. So I'm going to use a few more slides to kind of get after this. So let's say we've achieved equilibrium and then we add more mass, either more protein or more ligand to the system, especially on the left side. So we're going to add more unbound protein, unbound ligand / substrate on this side. Now we've got more mass on this side, and law of mass action says we are going to try to get it back to equilibrium. All right. The rate of association will increase to shift it to get back to that percentage, right? Law of mass action is trying to achieve equilibrium, and this percent here is dictated by affinity. And so by adding mass on the left side, specifically in this situation, what's going to happen? Adding unbound either protein or ligand or both leads to an increase in the rate going to the right, so that we get that, again, that magic percentage of equilibrium. So when we add or subtract mass on either side of this equation, that will affect the rate of whether something is associating or dissociating. Again, law of mass action says that we will attempt to achieve that percentage for that given reaction. This KEQ is that ratio between bound versus unbound, okay? And that is a function of affinity. Now, this is KEQ, not to be mistaken for KD, which we're going to talk about in a couple of slides. But before we go there, this is a really, really awesome visual site for illustrating this. The reason we even go to the math is because it's hard to draw this stuff out all the time. But in this case, they've created a really, really cool website. Let me show you a picture of this in the next slide. And so this is an interactive website where you can actually move these sliders around, change the amount of A, which is in red, change the amount of B, which is in green, all right, and the amount of product or the bound form in this case. So you can be either way. It could be the product, it could be the bound form, and shows you what it would look like at equilibrium. And you can change those around, and you see how the ratio changes as you change mass. That's law of mass action. Give it a shot. It's really cool. So that percentage between bound and unbound form is a function of affinity. Now, I don't know the reasons behind this, but in the previous slides, they use KEQ, and then we have this thing called KD, and they're basically flipped ratios. So if I show you the picture here, KEQ would have this on top and this on bottom. KD, they're flipped. They're inverses of each other. So the dissociation constant, the KD, the number smaller is stronger. That's because the ratio of unbound is less to the ratio of bound. That's affinity. Competitors and inhibitors, those things can, when we talk about drugs and so forth, depending on how potent a drug is a function of affinity. Same thing too with ligands and things that activate function in the cells. A higher affinity means it's more likely to bind, more likely to activate, et cetera, et cetera. Reminder here, and this is the last thing today. I'm not asking you to actually do any of the math or make any of the calculations, but it is important that you understand what the concepts are talking about. In this case, we're talking about how strongly the protein wants to bind to the ligand or the substrate. In the case of the KEQ, we're talking about the ratio of how much is going to be bound and unbound. All right. So focus on the conceptual understanding, because that's where we're going to go. We're going to try to avoid doing math throughout this class, but we are going to do concepts. And so understanding how affinity and law of mass action are related is something to work on. And so that concludes this lecture. I hope you've gotten some information. I hope you've taken good notes, because notes help you to avoid having to spend more time than you need to. So thank you for your time. If you have any questions, I will see you in class. Take care.